In this video, we're going to continue our notes on section 2.1 and 2.2 on elementary derivative rules. So now we're going to get into looking at this list of shortcut formulas for computing derivatives of various functions. But before we do that, I want to look back at a function and recall how we, so far in this class, have computed the derivative of it. So suppose we're given f of x equals x squared plus 3, and we want to find f prime of x. So let's just recall how that went. So we use the limit definition of the derivative, and that is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So for us, with the function f of x equals x squared plus 3, we just plug in x plus h into our function, subtract plugging in x, and divide by h. So we can just quickly go over what that would look like. So for us, this would be equal to the limit as h goes to 0 of x plus h squared plus 3 minus x squared plus 3 all over h. So how we handle this limit? Well, we can't just plug in h equals 0 yet. So what we do is we have to expand that numerator and hope that some things cancel. Turns out they will. So let's see that in action. So in that numerator, we first FOIL this x plus h squared term, and that becomes x squared plus 2xh plus h squared. Then we're going to subtract, well, first I need to add that 3. Then we're going to subtract that last part. So now we're going to have negative x squared, negative 3, or minus 3 all over h. And I don't want to forget my limit as h goes to 0. So now what do we notice? Well, the 3's cancel out. The x squareds cancel out. And in the numerator, we're just left with the following. So this is equal to the limit as h goes to 0 of 2xh plus h squared all over h. And what do we notice? But each term in the numerator now has an h, and we can cancel that h with the denominator. So this becomes the limit as h goes to 0 of 2x plus h. Now it's okay to plug in h equals 0 because this is a continuous function. So when we do that, we get 2x plus 0, which is equal to 2x. So in summary, what we found was that f prime of x is equal to 2x. And this is for the function f equals x squared plus 3. So for us, when our original function just had a x squared term plus some constant, 3 is just a fixed number, so it's called a constant, the derivative using this formula worked out pretty nicely. What about more complicated functions? So let's now just look at one more example. Using a slightly more complicated example. So let's suppose now we're looking at the function f of x equals x cubed. So it's not a completely super more complicated function. We're just having exponent of 3 instead of 2. So if we wanted to compute the derivative here using the limit definition, we'd have to set up the limit as h goes to 0 of x plus h cubed minus x plus h all over h. Again, just setting up that difference quotient. But now we have to compute a cube here, which would involve doing the multiplication x plus h x plus h times x plus h, foiling, foiling again, and it would get super messy and lots of algebra. Super messy. Not like we can't do messy things, but sometimes our time is better spent elsewhere. So mathematicians have come up with formulas for derivatives of some common family of functions, like power functions, where we have a variable in the base and a power in the exponent. How they came up with these formulas is by doing a lot of work with super messy algebra and also using constants instead of numbers. So maybe putting an n here to represent any fixed number, working out the formula here, and then finding a general form for derivatives of functions that look like this. So that's kind of the backstory of how we're going to get some of these shortcut derivative formulas. So now let's take a look at those formulas and write some out. So the first derivative we're going to look at is the derivative of a constant function c. So note here, c is a constant. And this one you might be able to think of on your own. So the function c is just a function where the output at any x value is just c. So what do we think the slope of that function is at any point? Or rather, what does the derivative look like? Well, the derivative is always going to be 0 because the tangent line at any point on a curve here is always a horizontal line, which has a 0 slope. So then what about for the functions that we just looked at in our little warm up for a power function x to the n? So it turns out what we get for such a derivative looks like n times x to the power of n minus 1. So if n is your exponent, the derivative, we have n drop down, and your exponent is 1 less than it was before. So this formula here is often called the power rule. This is called the power rule. So when we compute derivatives of some functions, I might say something like use the power rule. And note that this only works for constant exponents. Meaning n has to be a fixed constant or a fixed number, if you'd like. So let's do some examples while we're here. So example. So let's consider the function f of x equals x cubed, like we were just trying to work on. But now look, I'm only leaving a little bit of space for ourselves because we actually don't need to do too much. We don't need the limit definition anymore. We're just going to use the power rule. So here, using the power rule, the derivative becomes, well, that exponent is going to come down and be in front of the x term. And then the exponent is going to drop by 1. So that just becomes 3x squared. Not too bad. Let's look at one more. What about g of x equals x to the 1/2? So here our exponent is 1/2. It's still a constant fixed number, so the power rule can work. So here the derivative is going to be, well, I'm going to have the power come down, be multiplied in front of the x. So I'm going to get 1/2 times x. Then my exponent is going to be 1 less than it was before. So I'll have 1/2 minus 1. So we can clean that up a bit. So I have x over 2, because that 1/2 is the same as dividing by 2, to the power of negative 1/2. Again, 1/2 minus 1 is just negative 1/2. And now we can even simplify further to get rid of a negative exponent. That entire term comes to the denominator. So this is going to be 1 over 2x to the 1/2. And then a fractional exponent is the same as a root. So if we have a 1/2 exponent, that's equal to square root. So this term is equal to 1 over 2 square root of x. So there we go. Derivative of the function g of x to the 1/2 is equal to 1 over 2 root x. In some of your homework problems, you're going to see some examples of this, so you'll get more familiar with doing these computations. And just to follow up real quick here, so the original function g of x, it was written with a fractional exponent, but as I just stated, a 1/2 exponent is equivalent to the square root. So what we just found is the derivative of the square root function is equal to 1 over 2 root x. All right, so let's look at a couple more now. So now we're looking at, in number 3, an exponential function, meaning the exponent is a variable and a is a fixed constant. So the formula here is going to be the following: a to the power of x, so the same term, a to the x, same function, but then we multiply by ln natural log of a. So if you haven't seen natural logs or logs in a while, it might be a good time to review just a bit of some properties of logarithms. I'll have a link to a couple videos if you just want a quick review on those. And as you work through examples, you can get a feel for the log or the natural log by just working through these formulas a few times and dusting off some of your understanding for it. Number 4 looks at the derivative of the exponential function e to the x. This one you all will love. It's just e to the x, which is super cool because what it means is the change of the function e to the x at any point is equal to the value of that function itself. Whoa, that might take a little bit to sit in. But for now, feel free just to write that in your notes, to write this shortcut in your notes. The more we use it, the more we'll start to appreciate it. So now we look at a few different formulas that are similar in that they use operations. So number 5, we're looking at multiplying a function by a constant. So C is a constant. So it's a fixed number. So if we multiply a function by a fixed constant, then the derivative is just going to be that constant times the derivative of the function. So the derivative of a constant times a function is equal to the constant times the derivative of that function. So in a sense, the constants kind of factor out of the derivative. In number 6, we're looking at a sum of two functions. So it turns out derivatives behave very nicely with sums and differences. So the derivative of a sum of two functions is just equal to the sum of the two derivatives. So f prime of x plus g prime of x. And similar story goes with a difference. So the derivative of a difference of two functions is equal to the derivatives or the difference of the derivatives. So f prime of x minus g prime of x. So we should have this entire box filled in at this point in the video. And before we finish, let's just look at one more example using some of these rules. All right. So here's an example. So let's look at the function h of x equals x to the 4 minus 2x cubed. So we're going to find h prime of x, the derivative. So first of all, we notice that h includes a difference of two smaller functions, x to the 4th and 2x cubed. So what we can do when we're computing h prime of x, using this rule number 6, we know, oops, not 6 though, we have a difference, so we're using rule number 7. We know that in order to compute the derivative of our entire function, we just need to compute the derivatives of each term. So x to the 4th, I need to compute the derivative of x to the 4th. Then I'm going to subtract the derivative of 2x cubed. So now we see in the first term, we just have a power function going on. So which rule are we going to use? The power rule, number 2. So that says that the derivative here is, I'm going to bring that 4 down and then subtract 1 from the exponent. So that looks like 4x cubed. Now this second term, I have a 2 times a power function. So we know that if we just have a 2 that we're multiplying our function by, we saw in this rule 5 that that 2 can just come out. And now I just need to compute the derivative of that power x cubed. So now we just use the power rule again. So I'm going to have 2 times that exponent's going to drop down, and I'm going to subtract 1 from the exponent to have an exponent of 2. So let's clean this up a bit. So I have my first term minus my second term. So that's going to be equal to 4x cubed minus 2 times 3 is just 6x squared. So my derivative, h prime, is equal to 4x cubed minus 6x squared. So at this point, it might look like there's a lot going on here, a lot of moving parts, but the more of these functions that you compute the derivatives of, the quicker it will feel. You'll become really good at being able to identify which function, which rule here to use. And it will almost get to a place where you don't even have to think back to the rule. You just kind of have a routine down. But it's going to take a lot of work looking at a lot of questions in order to get that practice down. All right, thanks for watching this video, everyone. And meet me at the next video for our example 1 in our notes.